Hello everybody, welcome into another lesson. So today we are going to talk about trigonometry and vectors. So how we're going to start is we're going to talk about finding a magnitude and a direction angle of a vector. The goal of this is to figure out what angle does a particular vector make with the positive x-axis, going the normal counterclockwise route. Now, to find the vector itself is the magnitude of that vector times the cosine of theta I plus the sine of theta j. Or it could be the magnitude of the vector. This is the linear combination form. It could also be the magnitude of the vector times the cosine of theta and then sine of theta in component form. Either way would give you the exact same result. So let's do some examples here and see what we got. So for the first one, vector v has a magnitude of 5 times the quantity of the cosine of 30 degrees I plus the sine of 30 degrees j. So, as you see in the parentheses, this is in linear combination form, which is still a very valid form for the vector. They want you to find the magnitude and direction angle of this vector v. Well, in this form, they give it to you. The magnitude is 5. That's pretty easy. That's outside of the parentheses. The magnitude itself is 5. That much is pretty easy. And then the direction angle is also given to you. It's 30 degrees. So it makes a 30-degree angle with the positive x-axis. So in this form, you have your magnitude and your direction angle handed to you. Pretty simple there. Let's do one more like this, and then we'll do a few where we got to find both. Now let's say I have 8 times the quantity of the cosine of 135 degrees I plus the sine of 135 degrees j. Well, find the magnitude and direction angle. Well, the magnitude's outside of the parentheses, so that's also pretty easy. The magnitude of v is going to be 8. That one was handed to you. And then inside the parentheses, you have 135 degrees. So your direction angle that it makes with the positive x-axis is 135 degrees. So this vector has a magnitude of 8 with a direction angle of 135 degrees. Pretty simple. Now, on the other hand, let's say we get into, what if they just give it to you like this? You have 6i minus 6j. Alright, so they give it to you in a normal linear combination, no angles. You want to find the magnitude and direction angle. Well, we could definitely start out finding the magnitude. So the magnitude of vector v, that's going to equal the square root of that 6 squared plus that negative 6 squared, which would give you the square root of 36 plus 36, which would end up giving you the square root of 72. Which would end up giving you, let's see, trying to think of the best way to break this down. You have 36 times 2, which would end up being 6 times the square root of 2. So the magnitude of this particular vector is 6 times the square root of 2. We found the magnitude. Now let's find the direction angle. So in general then, we know that it's going to be a cosine of theta plus a sine of theta, right? Well, in order to find the total angle, you're going to need to take the tangent of theta, set that equal to your y-coordinate, which in this case is the sine of theta, over the cosine of theta, which would end up giving you -6/6, which would give you -1. So now you just have to take the tangent inverse of -1. You got the tangent of theta equals -1. Now, if you look at your original vector, this is going to help us identify what quadrant we need to be in. Your x component's positive, your y component's negative. So x is positive and y is negative in the fourth quadrant. So this will be based on a tangent of theta in the fourth quadrant. Subtract 45 degrees from 360, you would get 315 degrees. So the angle it makes with the positive x-axis and the direction angle is going to be 315 degrees. So the magnitude of this vector is 6 times the square root of 2. The direction angle is 315 degrees. I got more of these. Alright, so vector v is -4i minus 7j. So vector v is equal to -4i minus 7j. Probably best if we find the magnitude first, right? That's going to be the easiest. Take the magnitude of v, so that's going to be the square root of that -4 squared plus that -7 squared, which is going to give you the square root of 16 plus 49, which would give you a magnitude of the square root of 65. So the magnitude of this particular vector is the square root of 65. Now we need to find the angle. So we're going to take the tangent of theta, set that equal to our y component of the vector, -7 over -4, which would be positive 7/4. So the tangent of theta equals positive 7/4, so we're going to take the inverse tangent. Now, here's the thing. If we look at our original vector, both your x and your y components are negative, which means it's going to be in the third quadrant. So we're actually going to have a third quadrant angle. When you take the inverse tangent of a positive number, you end up in the first quadrant. So whatever result we get, we're going to have to add 180 degrees to that. So if you take the inverse tangent of 7/4, you initially get 60.255118, so on. But if you add 180 to that to get you the third quadrant, you get a reference angle of approximately 240.26 degrees. Not a reference angle, a direction angle, excuse me. So the magnitude of this vector is going to be the square root of 65. The direction angle for this vector is 240.26 degrees. And again, you have to bear in mind what quadrant you would be in, because we're going to assume all of these vectors' initial points as starting points at the origin. So that's probably the best way to do it. Got 2 more of these, then we got other types to do. Alright, v is equal to -2i plus 5j. All right. So vector v in the linear combination form is negative 2i plus 5j. So let's find the magnitude of vector v. Magnitude is equal to the square root of that negative 2 squared plus that 5 squared, which would turn into the square root of 4 plus 25, giving you the magnitude of the vector to be the square root of 29. So the magnitude of vector v ends up being the square root of 29. Now let's find the direction angle. So you'll take the tangent of theta is equal to that y component of 5 divided by the x component, which is negative 2, which would give you negative 5 halves. So the tangent of theta equals negative 5 halves. Now let's look at the original vector. The x component is negative, but the y component is positive. X is negative and y is positive in the second quadrant. So when we take the inverse tangent of negative 5 halves, we normally end up in the fourth quadrant. You're going to actually get a negative angle. So take the tangent inverse of negative 5 halves, you get about negative 68.2. Well, if you add 180 to that, you'll end up in the second quadrant with a direction angle of about 111.8. So the direction angle for this vector is going to be approximately 111.8 degrees. Again, understanding which quadrant you're in, that's the biggest key to this. One more of these and then we'll move on to other types here. They're actually taking it pretty easy this time. Vector v has linear combination 12i plus 15j. Well, it's definitely going to be in the first quadrant, so that's going to make everyone's life a lot easier. But let's go ahead and find the magnitude of this vector. Well, that's going to end up being the square root of that 12 squared plus that 15 squared, which would equal the square root of 144 plus 225, which would end up giving you the square root of 369. Which, does that break down any further? I want to say it does. Which would turn into 3 times the square root of 41. So the magnitude of this vector is going to be 3 times the square root of 41. Now let's find the direction angle. So you'll take the tangent of theta, set that equal to your y component of 15 divided by 12, which would simplify into 5/4. Well, we take the tangent inverse, we'll end up in the first quadrant, and we already are in the first quadrant, so we'll get the direct angle. We'll get an approximation to 2 decimal places. Take the tangent inverse of 5/4. You get an angle of approximately 51.34 degrees. So the direction angle for this vector is approximately 51.34 degrees, making that angle with the positive x-axis. Okay. So now we're going to, now for the next exercises, we're going to be given the magnitude of a vector and the angle it makes with the positive x-axis, and we need to find the component form. So find the component form of the vector given its magnitude and direction angle it makes with the positive x-axis. So that would be an angle in standard position, because the angles that we think of make an angle with the positive x-axis. So it's your classic type of angle. So you're given, in this case, a magnitude of vector v having 3. The direction angle is going to be 30 degrees. Not 30, 0. I don't know where I'm getting 30 from. Theta is 0 degrees, okay? So, remember how I said earlier in the lesson that vector v in trigonometric form can be expressed as the magnitude of vector v times the quantity. It becomes a scalar multiple, that magnitude does, of the cosine of theta and then the sine of theta in component form. Okay, so if we apply that in this case, vector v would be the magnitude of 3 times the cosine of 0 degrees, the sine of 0 degrees. Well, okay, so let's keep that 3 on the outside for a minute. What is the cosine of 0 degrees? That's just 1, right? Sine of 0 is 0. Now if I just take that scalar multiple of 3 and distribute that through the vector, you'll get in component form that vector v is going to be 3, 0. So in component form, vector v is 3, 0. So this is partly how trigonometry relates to vectors. All right, we got the magnitude of vector v in this case is equal to 1. We got that the direction angle is 45 degrees. So vector v is going to be equal to that scalar multiple of 1, which 1 times anything is itself. So we can go straight to figuring out the cosine of 45 degrees and the sine of 45 degrees. Well, vector v then, cosine of 45 is the square root of 2 over 2. And it actually happens that the sine of 45 is also the square root of 2 over 2. So that's going to be your vector in component form. Vector v would be square root of 2 over 2, square root of 2 over 2. Let's see what we're getting into here. All right, this time we have a magnitude of 3 times the square root of 2. We have a direction angle of 150 degrees. So to find this in component form, vector v is going to equal that magnitude of 3 times the square root of 2 times the vector of the cosine of 150 degrees times then the sine of 150 degrees. Well, let's simplify this. Keep that scalar multiple of 3 times the square root of 2 on the outside of the vector, all right? Cosine of 150 degrees, we know it's in the second quadrant. That's going to be a 30-degree reference angle in the second quadrant. The cosine of 30 is normally square root of 3 over 2. Since it's in the second quadrant, that would actually be negative square root of 3 over 2. And then you have the sine of 150. Well, that's going to be a 30-degree reference angle in the second quadrant. That would be positive 1/2. So now you distribute that scalar multiple, you'd end up with the vector being negative 3 times the square root of 6 over 2, and then 3 times the square root of 2 over 2. That's exactly how you would find the vector in component form. You would end up getting negative 3 times the square root of 6 over 2, 3 times the square root of 2 over 2. All right, this magnitude is going to be 4 times the square root of 3. The direction angle is 90 degrees. So we have a 90-degree direction angle. Magnitude is 4 times the square root of 3. So vector v can be written as that magnitude of 4 times the square root of 3 times the quantity of the vector of cosine of 90 degrees, then the sine of 90 degrees. Well, keep that scalar on the outside of that 4 times the square root of 3, so what's the cosine of 90? That's just 0. Sine of 90 is 1. So now you just have a scalar multiple of 4 times the square root of 3 times vector 0, 1, giving you your vector in component form being 0, 4 times the square root of 3. That's exactly what you would get. 0, 4 times the square root of 3. Two more of these and we got something else. Magnitude of the vector is 2. All right, let's see. V in the direction of I plus 3j. So they didn't give you the direct angle this time. This time they gave you the magnitude of the vector, and then they said that vector v is in the direction of I plus 3j. Well, we're definitely going to need to find its angle. So we notice though that I plus 3j, that's in the first quadrant. So this should give us a first quadrant angle. This won't be too bad. So let's find that direction angle first. So that's going to be the tangent of theta equals your y component of 3 divided by your x component of 1, or simply the tangent of theta equals 3. So that means then that theta equals the tangent inverse of 3, which should put us in the first quadrant, which is where we need to be. Tangent inverse of 3 gives you about 71.57 degrees. Now we've identified our direction angle, okay? Now let's go ahead and do the component form. So vector v would be approximately, and I'm saying approximately because the angle was approximate, that magnitude of 2 times the vector of the cosine of 71.57 degrees, and then the sine of 71.57 degrees. So this would be approximately 2 times, let's figure out what those are going to be. Again, these are going to be approximates because the angle was approximate. Alright, so to 2 decimal places, this is about 0.32 for the cosine of 71.57. What about the sine of 71.57? I get about 0.95. So we should be able to finally distribute that to, which should give you approximately a vector of 0.64, 1.9 for the vector and component form. You should get about 0.64, 1.9. I got one more like this, and then we're moving on to another topic in this lesson. Alright, so this time they give you that vector v has a magnitude of 3 and vector v in the direction of 3i plus 4j. So we need to find the direction angle for vector 3i plus 4j. We already know the magnitude, but now we need to find the direction angle. Good news is you have a positive x and a positive y component, so it's going to be in the first quadrant. So take that tangent of theta, set that equal to your y component of 4 over your x component of 3. So then now to find theta, you'll just take the tangent inverse of 4/3. We should be able to get a 2 decimal place approximation. And you would get about 53.13 degrees. So the direction angle is approximately 53.13 degrees. Okay. Now to find the component form of vector v, that's going to be that magnitude of 3 times the vector of the cosine of 53.13 degrees, then the sine of 53.13 degrees. Which this is going to turn into, and I should say this is approximate because the angle is approximate. So this is approximately equal to 3 times whatever those values are. Wow, it rounds to 0.6 for the cosine of 53.13. That is actually a lot better than I thought. And you get about 0.8 for the sine of 53.3. So you distribute that 3 in component form, you get a vector of about 1.8, 2.4. That would be the component form of this vector. You would get about 1.8, 2.4. Okay, so that's finding the component form of a vector given the magnitude and the direction angle. Now, what we're about to do is find the component form of the sum of two vectors giving their magnitudes and direction angles. So basically we're going to do this with two vectors now. So let me write out what the objective is here. Find the component form of vector u plus vector v given their magnitudes and direction angles theta sub u and theta sub v. Alright, so find the component form of vector u plus vector v given the magnitudes and direction angles theta sub u and theta sub v. Well, let me set this up here. So we are given that the magnitude of vector u equals 5. The magnitude of vector v also happens to equal 5. They also give you that theta sub u equals 90 degrees. Theta sub v is equal to, the theta sub u was 60. I had it backwards. Theta sub u was 60. Theta sub v is 90 degrees. Okay. So what we need to do here for each of these vectors to start with, find their component forms. And then once you've done that, you can go ahead and add the results. So let's work on finding vector u itself. Vector u equals that magnitude of 5 times then that direction angle for u, that theta sub u is 60 degrees. So that would be times the cosine of 60 degrees. And then you have the sine of 60 degrees. Okay, so this is going to end up equaling 5 times, now what is the cosine of 60? That's just 1/2. The sine of 60 is the square root of 3 over 2. So that means that vector u itself is going to end up being 5/2, then 5 times the square root of 3 over 2. So there's your vector u. Let's go ahead and find vector v. That equals the magnitude of v, which I didn't specify that was also 5. That's also 5. This case times the cosine of theta v, which is the cosine of 90 degrees, then the sine of 90 degrees. Well, this would turn into 5 times, now what is the cosine of 90? That's just 0. And then the sine of 90 is 1. So this would just end up being 5. I'm sorry, this would end up being 0.5, which equals vector v. Vector v is 0.5. Now we found the component form of both vectors. All we got to do is take them and add them. So u plus v equals that vector 5/2, 5 times the square root of 3 over 2, plus the vector 0, 5, which would end up giving you a total vector of 5 halves. And then, well, 5 plus 5 times the square root of 3 over 2. That would be your vector, the sum of the two vectors in component form. So you end up getting 5 halves and then 5 plus 5 times the square root of 3 over 2. And I got 3 more examples like this. Why don't I move this a little bit closer, huh? Magnitude of u is 2. The magnitude of v is also 2, which makes our lives not so bad. Theta sub u is 30 degrees. Theta sub v is still 90 degrees. Okay. So again, ultimately we want to find the sum of vectors u and v in component form. And we were given the magnitudes of each and their direction angles. So first thing we need to do is find the component form of each individual vector. So let's work on vector u. That's going to equal that magnitude of 2 times the cosine of theta sub u, which is 30 degrees, sine of theta sub u, which is 30 degrees, which is going to end up giving you 2 times. Now, what is the cosine of 30 degrees? That's the square root of 3 over 2. And then the sine of 30 is going to be 1/2. Giving you a total vector u of simply the square root of 3, 1. Now we need to do the same for vector v. So vector v, the magnitude of v was 2, times this time the cosine of theta sub v was 90, so the cosine of 90, and then the sine of 90. Alright, so keep that 2 on the outside of the vector. What's the cosine of 90? That's just 0. The sine of 90 is 1. You distribute that 2 through the vector, multiply it, you end up getting a total vector v of 0, 2. Now that we've found both individual vectors, all we have to do is add them. So take u plus v. That's going to be equal to the square root of 3, 1, plus 0, 2, for the final result being the square root of 3, 3. So that's the sum in component form. You get the square root of 3, 3. I got 2 more of these, and then we got 2 final exercises after these, which are different altogether. All right. These are more than likely going to change. All right, they do change it. Magnitude of u is 20, magnitude of v is 50. Theta sub u is 45 degrees. Theta sub v is 150 degrees. They really pulled the rug out from under you this time. Well, still, first thing we need to do is find each individual vector. So vector u is going to end up equaling that magnitude of 20 times the vector of the cosine of theta sub u, which is 45 degrees, and then the sine of 45 degrees, So this would turn into 20 times, what is the cosine of 45 degrees? That's the square root of 2 over 2. And the sine of 45 degrees is the exact same. Square root of 2 over 2. Once you multiply that 20 through, you'll just end up getting a vector of 10 times the square root of 2, 10 times the square root of 2. All right, so there's your vector u. Let's find vector v. Vector v has a magnitude of 50, so take that 50 times, let's see, the vector of the cosine of 150 degrees, and then the sine of 150 degrees. So that's going to equal 50 times whatever these results are. Okay, 150 degrees is the same thing as a 30-degree angle in the second quadrant. Well, the normal cosine of 30 is the square root of 3 over 2, but since it's in the second quadrant, that would be negative square root of 3 over 2. And then the sine of 150, that's the sine of a 30-degree angle in the second quadrant. That'd be positive 1/2. Which for the final result for vector v would simplify into negative 25 times the square root of 3, and then 25. So now we just need to add vectors u and v, and this is about to get to be real fun. We're going to have a very hideous result. In component form, you add your x components to each. You'll end up getting 10 times the square root of 2 minus 25 times the square root of 3. That's just for your x component of the vector. And then for your y component, you'll end up getting 25 plus 10 times the square root of 2. So yes, you can get vectors like that. That is the sum of vectors u and v. And I got one more of that, and then we're on to the final two exercises. Alright, what do we got? Vector u has a magnitude of 35. Vector v still has a magnitude of 50, but I'm sure the angles have changed. Oh yeah, they have. The reference angle for theta sub u is 25 degrees. Theta sub v is going to be 120 degrees. Well, we have a 25 degree angle, right? Which is definitely not a special angle, which means we're very likely going to end up with decimal approximations. So I say we just take decimal approximations for all of these. Even though 120 degrees is a special angle, 25 isn't. So nonetheless, let's go ahead and proceed with finding each vector. So vector u equals that magnitude of u, which is 35, times the vector of the cosine of theta sub u, which is the cosine of 25 degrees, then the sine of 25 degrees. So that would be 35 times now whatever these are going to be. I'm going to round to 2 decimal places. You get about 0.91 for the cosine of 25. What about the sine of 25? You get about 0.422. Or 0.42. Yeah, we'll do 0.42. which for our final result here, let's take 35 and multiply each of those numbers. So about 31.85. And then take 35 times 0.42. Get about 14.7. Alright, so there's your vector u approximately. Let's do vector v approximately. The magnitude of v was 50, so take 50 times the cosine of 120 degrees, and then the sine of 120 degrees, which would be approximately equal to 50 times, well, the cosine of 120, that's a 60-degree reference angle in the second quadrant. That would end up being negative 1/2. So negative 0.5. That one was easy, but the sine of 120 is going to be the square root of 3/2. Which is approximately 0.87. So now we just multiply that 50 through the vector and we should get an answer. So you end up getting negative 25 for the first number, and then take 50 times 0.87. You get about 43.5. So now we can just add vectors u and v. So add each of these here. So take that 31.85 minus 25, and then that 14.7 and 40 plus 43.5. Well, that should end up being 6.85 for the x component. But your y component's going to be bigger. That's going to be fun. Your y component, you get about 58.2. So for the end result, for vectors u plus v, you end up getting about 6.85, 58.2. All right, last two exercises, and these are going to be finding the angles between vectors. We are going to find the angles between vectors. All right, so let's see. We have a vector v equals I plus j. Then we have a vector w is equal to 2 times the quantity of I minus j, which I think it's safe to say we just want to distribute that 2 through. That would end up being 2I minus 2j. All right, we want to find the angle between these vectors. So let's draw some vector v. There's vector v, right? I plus j. From here, that'll be your vector w when you add vector w to it, which is 2I minus 2j. The idea is we can find that angle theta between these vectors. Well, how, might you ask? Well, we need to find the length of v and the length of w for sure. The length, that's simply the magnitude. So let's take the magnitude of v, right? The magnitude, that's just going to be the square root of 1 plus 1, which would give you the square root of 2. So we know this has a length of the square root of 2 for vector v. Now vector w, let's do the same thing. Take the magnitude of vector w. That would equal the square root of 4 plus 4. That's going to equal the square root of 8, which would be 2 times the square root of 2. So vector w has a magnitude of 2 times the square root of 2. We could treat these magnitudes as lengths. Well, it looks like we have a side angle side triangle minus a third side. And in that case, we could apply the law of cosines to find this angle. There's just one problem. We don't know the length of the third side. Well, that's where you're going to simply add vectors v plus w. All right, so do your vector addition. Take vector v plus w. You'll end up adding each of your components, your I plus 2i. You'll end up getting 3i. And then take your j minus your 2j. That would be minus j. So we found vector v plus w. Here is that side. Here is vector v plus w. Now we actually have the third side. That means all we need to do now is find the length of the magnitude of v plus w. So the magnitude of v plus w, that's going to equal the square root of 9 plus 1, which would give you the square root of 10. So the magnitude is equal to the square root of 10. Now we know all three sides, and between two of the sides we know an included angle. We can proceed to use the law of cosines. So why don't we call this C for simplicity's sake? We'll call that B. We'll call that A. And then that theta will be C. We're going to use the law of cosines for the C squared equals A squared plus B squared minus 2AB cosine of C. Alright, so that C we've determined is that V plus W. That's going to be that square root of 10 raised to the second power. That would equal our A, which is that magnitude of V. That'd be the square root of 2 raised to the second power. Plus that B, which we determined was the magnitude of W. That would be 2 times the square root of 2 raised to the second power. Minus 2 times the square root of 2 times 2 times the square root of 2 times the cosine of C. So that means 10 is going to equal 2 plus 8 minus 8 cosine of C. So that means that negative 8 times the cosine of C equals 0. You'll get that the cosine of angle C equals 0. Well, this one we don't even really need to apply the inverse. It should be pretty obvious that the cosine, anywhere you have a cosine of 0, it'd be 90 degrees. So in this case, that angle between the two vectors is going to be 90 degrees. So we actually happen to have a right angle between the two vectors. And you can apply this with lines in general. You'll just have to use the distance formula to find the length of lines. But it's a little bit easier with vectors to find the angle between two vectors. I got one more of these exercises. I think I'm going to keep the triangles up, keep that up, because we'll even use the same law of cosines formula. I'll keep us set up here, but we should definitely get a different angle this time. Alright, so we're given that vector v is equal to 3i plus j. Vector w is 2i minus j. So we want to find the angle between vectors v and w. So ideally you want to apply the law of cosines to be able to solve for that angle. So we need to find some lengths, which in this case are magnitude, since we're talking about vectors. Magnitude, length, you could use them interchangeably. So vector v is 3i plus j, so that's going to be the same as 3 squared of 3 squared, which is the square root of 9, then plus a 1. So vector v has a magnitude of the square root of 10. Then let's find the magnitude of w. That's going to equal the square root of that 2 squared, which is 4, then plus a 1. That would just be the square root of 5. Alright, so vector w equals the square root of 5. Now, of course, in order to make this law of cosines application work, we need to find the length of the third side, or the magnitude of that, which would be the magnitude of v plus w. So let's add these two vectors first. V plus w, that itself is going to be 3i plus 2i, that ended up being 5i. Then j minus j, that's 0. You'll literally just get 5i. So if you want to apply the magnitude of v plus w, that's going to equal the square root of 5 squared, which is simply 5. So you actually get the whole number 5 for the magnitude of v plus w. Now that we know all three sides, we can use the law of cosines to find this angle. So again, let's call v, the magnitude of v, we'll call that a. We'll call the magnitude of w b. We'll call the magnitude of v plus w c. And then we'll call theta will be equal to angle c. That'll make our lives a lot easier. So c squared, which in this case is going to be 25, equals a squared, which is a square root of 10 squared, that'd just be 10, plus b squared, which is square root of 5 squared, that'd just be plus 5, minus 2 times a, which is the square root of 10, times b, which is the square root of 5, times the cosine of c. So that would mean that negative 2 times the square root of 50 cosine of c equals 10. Let's see, so that would end up meaning negative 10 times the square root of 2 cosine of c equals 10. Not 0, I wish it were that easy. Which means the cosine of c equals negative of the square root of 2 over 2. Well, we're going to end up having the inverse cosine of a negative value, which would put us in the second quadrant. And I guarantee you, if you took the inverse cosine, you would find it came up 135 degrees, which is exactly what it is. So that means that angle between these vectors v and w, that direction angle, is going to be exactly 135 degrees. So that is the angle between vectors v and vector w, is 135 degrees. Alright, so that's it for this lesson. Next lesson we're going to talk about vectors and dot products of vectors, which that'll enable us to determine if vectors are perpendicular is by finding the dot product. So I hope everyone has a great day. Take care.